Hello everyone, myself Surya Narayan Panda, a senior research fellow at SN Bose National Center for Basic Sciences, Kolkata. Here I work under the supervision of Professor Ranjan Barman in Spintronics and Spin Dynamics group. Today I am going to present my work on the crystal structure dependent interfacial spin transparency in tungsten CoFeB thin films. I have taken thin films because this type of heterostructure is used in magnetic data storage and memory devices for achieving faster operating speed, small devices with reduced power consumption, and reliable signal processing. Also, this type of heterostructure shows interesting spin-based effects like spin Hall effect, spin orbit torque, magnetic anisotropy, and Gyrosinski-Moria interaction. Usually, the spin orbit effects like spin Hall effect and the spin pumping are measured by electrical detection technique like spin torque ferromagnetic resonance, which suffers various ambiguities like large area averaging, which causes overestimation of the damping, and complicated microfabrication. In our lab, we have developed a all-optical method which is non-invasive and a local technique, so no complicated microfabrication is required, and damping here can be directly extracted from the precessional dynamics data, and inhomogeneous effect due to large area averaging also can be easily avoided in this technique. We have able to measure the spin Hall effect using this technique, and most recently we have used this technique to measure spin pumping induced interfacial spin transparency at beta tantalum and CoFeB interfaces. Then what is special about tungsten? Tungsten shows a thickness dependent phase transition. At lower thickness it is in beta phase, which has a tetragonal A15 structure, but at the higher thickness it is in alpha phase, which has a body centered cubic structure. So in this work we are going to study the interfacial spin transparency at different crystal phase of tungsten by using a femtosecond laser based all optical technique. When a femtosecond laser falls on a magnetic material, the coherent interaction between the laser photon and charge and spin of the magnetic material causes the instantaneous thermalization of these charges and spins, which cause the instantaneous decrease of the magnetization of the whole system, which is called the ultra-fast demagnetization, and with time the energy is being exchanged with the lattice, which causes the fast remagnetization, and over time the whole energy is being transported to the surrounding, which resulted in magnetization, precision, and damping. We are mainly focused on studying this magnetization, precision, and damping, which is a nanosecond phenomena, by using time-resolved magneto-optical Kerr effect magnetometry. This is the schematic of the setup present in our lab, where the parent beam comes out of this Libra amplified laser system of 800 nanometer, and which is split into two parts. One part passes through the second harmonic generator, and the output of this second harmonic generator beam is used to excite the sample. We call it the pump beam. The other fundamental part pass through this variable delay stage and used to detect this excitation. We called it the probe beam. It falls on the sample normally, and we detect the data by using this lock-in amplifier and the LabVIEW software in phase sensitive manner. This is the photograph of the amplifier laser unit and the second harmonic generator in our lab, and this is the whole alignment of the TR-MOG setup. Here the red beams are the probe beams and the violet beams are the pump beams. And usually the TR-MOG data contains three regions. First region is the ultra-fast demagnetization region, the second region is the fast remagnetization region, and third region is the slow remagnetization with magnetization precision. We will mainly concentrate on the third region. Here the red line shows the bi-exponential background due to the slow remagnetization. And this background subtracted data is been fitted using this damped sinusoidal function, which gives us the tau, which is the precessional relaxation time, frequency f, and the Gilbert damping parameter alpha. The whole precessional dynamics can be explained by using this differential equation, which is called the Landau-Lipschitz-Gilbert equation. The first part is the precessional part, and the second part is the damping part. Going into few theoretical background, here we are going to study the spin pumping. What is spin pumping? When a ferromagnetic material is being placed adjacent to a non-magnetic material, due to the chemical potential difference of the non-magnetic material, the spin angular momentum flow from the ferromagnet to the non-magnet. The whole phenomena is called the spin pumping. It is mainly parameterized by two parameters. One is the spin mixing conductance, which determines the conductance property of the interface. Another is the spin diffusion length, which determines up to how much distance in the non-magnet the spin current can flow. When the non-magnetic layer thickness is less than the spin diffusion length, there is a back flow of the spin current, which is denoted here by the I is back, And in the right hand side, I have mentioned the spin diffusion length of few material where the graphene, which has very low intrinsic spin orbit coupling, shows very high spin diffusion length, and the platinum type of material, which has very high spin orbit coupling, shows very small spin diffusion length. In the presence of the spin pumping, the Landau-Lipschitz-Gilbert equation is got modified by addition upon this extra spin current term, which also resulted in the modulation of the Gilbert damping. Here the beta is the spin backflow factor and the epsilon here is the spin flip probability. So this modulation of the Gilbert damping can be modeled by using both diffusive and the ballistic spin transport model by using this formula. Here the G up down is the intrinsic spin mixing conductance which is taken into consideration of the spin backflow, and the G effective is the effective spin mixing conductance which taken into consideration of the spin backflow factor. And to calculate the interfacial spin transparency, which is a parameter that determines the effectiveness of the an interface or overall material, and we have used to calculate this parameter two model. One is the spin Hall magnet resistance model, another is the spin transfer torque based model. The spin Hall magnet resistance model are taken into consideration of the spin backflow, where the spin transfer torque based model does not take into consideration of the spin backflow. In an heavy metal ferromagnetic heterostructure, other than spin pumping, there is always possibility of presence of spin memory loss and 2-magnon scattering. So in our heterostructure that may be present. So to calculate their contribution, we have also fitted our experimental data by using a modified formula denoted by this, where the GSML is the effective spin memory loss conductance and the beta TMS is the coefficient of the 2-magnon scattering. This is our sample stack, where the tungsten is our non-magnetic heavy metal, where the cobalt iron boron is our ferromagnetic layer. We have varied the tungsten layer thickness from 0 to 50 nanometer, where the cobalt iron boron thickness is varied from 1 to 10 nanometer. Our sample is made by using RFDC magneton sputtering unit at a base pressure of 1.8 into 10 to the power minus 7 torr and the argon pressure of 0.5 milliliter. And these are few static characterizations. X-ray diffraction technique is being used to detect the crystal phase of tungsten, and from which we have found below 8 nanometer our tungsten is mainly in a beta phase due to appearance of highly intense 211 peak, and above 5 nanometer a small amount of alpha peak appears. This is 110 alpha peak. That's why the above 5 nanometer we called it in a mixed phase, alpha plus beta mixed phase. And the atomic force microscopy is used to calculate the roughness of our sample, which is comes out to be very small, around 0.2 to 0.3 nanometer throughout the thickness region. And the resistivity measurement shows a very clear change of the slope of the tungsten sheet resistance with tungsten thickness, where the below 8 nanometer mainly in the beta phase the resistivity of the tungsten is very high, about 287 microohm centimeter, than that of the mixed phase, which is about 112 microohm centimeter. And now coming into the dynamic measurement, these are the variation of the precessional dynamic with the ferromagnetic CoFeB thickness, and the right side shows the effective plot, the variation of the effective Gilbert damping with the inverse of cobalt iron boron thickness, the fitted with the both spin pumping and the modified formula by considering the spin memory loss and the 2-magnon scattering contribution. And from the fitting we obtained two things. First thing is that the effective spin mixing conductance, that is due to the spin pumping, is much higher than that of the spin memory loss conductance, and the 2-magnon scattering coefficient is very small, about order of 10 to the power minus 18. And from here we calculate the effective spin mixing conductance, and to calculate the interfacial spin transparency we need another parameter, which is the spin diffusion length, for which we have studied the precessional dynamics from different tungsten layer thickness. And this is the precessional dynamics due to the variation of the tungsten layer, and the right hand side shows the variation of the Gilbert damping parameter with the different tungsten layer, which shows a non-monotonic increase initially and then gets saturated and then decrease a little bit due to the thickness dependent phase transition of the tungsten. And we have fitted it by using both ballistic and the diffusive spin transport model by using these two formula. And from the fitting we mainly found that the spin diffusion length in both these model is about similar, about 1.7 nanometer per tungsten, where the intrinsic spin mixing conductance is slightly higher in the diffusive case. And after getting the spin diffusion length and the spin mixing conductance, we have calculated the interfacial spin transparency by using spin Hall magnetic resistance model and the spin transfer torque based model, and from which we have kept a very high interfacial spin transparency, about 80% for the beta phase of the tungsten, which is about 25% higher than that of the mixed phase. So there is a clear phase dependence of the interfacial spin transparency. Other than this, we have studied the variation of effective spin mixing conductance with the phase of the tungsten, which shows a distinct transition with the crystal phase of the tungsten. Also, we have obtained a dominant spin pumping contribution to the damping modulation in comparison to that of the spin modulus and the 2 magnum scattering contribution. So, other than spin pumping, spin modulus and the 2 magnum scattering, there is always a possibility of presence of other interface effects, that is due to interfacial band hybridization that may be present in a system. So to extract out this, we have introduced a copper special layer and varied its thickness from 0 to 1 nanometer, and we have not observed any damping modulation with this introduction of the copper and varying its thickness, which proves that these interface effects is very minimum in our sample set, which the main modulation of Gilbert damping which occurs is mainly due to the spin pumping. So now we are in our conclusion section. So we have able to accurately determine the interfacial spin transparency of the tungsten CoFeB by using a non-invasive all-optical method, and able to show that this interfacial spin transparency shows a dependence on the crystal structure of tungsten, and able to achieve a very high interfacial spin transparency. In fact, it is the highest reported value till date in the literature. It is about 80%, and this is a animation which shows the spin pumping induced interfacial spin transparency. When a ferromagnet CoFeB is placed adjacent to a non-magnetic material and it is been excited by the pump pulse, then this magnetization, the red arrow, is started to precess around this effective magnetic field, which is in the green arrow. It has been detected by this probe pulse. Then the spin current is been generated by the spin pumping, but not all the spin current is able to pass through this interface. Few are also blocked and get reflected, which determines the interfacial spin transparency of this interface. So these are few of my publications. This highlighted publication I just recently published, and show you the whole work. Now into the acknowledgement, I want to thank Professor Narayan Varman for giving me an opportunity to work in his lab. Also all of my lab mates for creating such an good and encouraging research atmosphere. And for this work I want to thank Sudhi Majumdar, Soma Datta, and Dr. Arpan Bhattacharya and Dr. Samiran Chaudhary. And at last I want to thank SN Bose National Center for Basic Science for the financial support and all the basic research facility. And thank you everyone for hearing me.